All right. Good day once again, and thank you for joining in to or coming to class, so to speak, an online class anyway. It's another time to push a step further on the series of topics that we've been treating on the chemistry JAMB syllabus, and today we are going to be looking at chemical combination. That's what we're going to be looking at as a topic today. We've considered some topics earlier, but venture you've not seen those videos, kindly look for them so that you can build up on the knowledge that will be shared in this video. All right, so like I said, today we are going to be looking at chemical combinations, and my name is Anjorio Luafemi Excel for those that are just joining us for the first time, and I hold a bachelor's degree in chemistry from the Premier University, University of Ibadan, and also a postgraduate degree in education, in science education to be precise, and majoring in chemistry as on my thesis for my project. I also hold a master's degree in environmental and analytical chemistry from the Redeemers University, Ede, Osun State. And I'll be your tutor, and I know that you will gain a lot from this class. All I just want you to do is pay close attention, get your writing materials beside you, your calculator too, because we're going to be doing some little calculations as we go along in this topic. So get your calculator ready, get your biro and your pen also available so that you can be able to do any class activity that I push forward to you to engage in. All right, without say, well, I haven't said that. Let's quickly move on to the learning objective for this particular topic. What is our learning objective? By the end of this lesson, it is expected that students should be able to explain the law of definite proportion. So students should be able to explain the law of definite proportion by the end of this lesson, and also describe the law of conservation of matter, not only explain the laws of definite proportion, but also the laws of multiple proportion and reciprocal proportions, and then describe the law of conservation of matter. It's also expected that by the end of this lesson, you should be able to understand the Lusak's law of combining volume and Avogadro's law. Okay, and also to interpret chemical symbols, formulae and equations, and to calculate the relative atomic masses based on carbon 12, and also to apply the mole concept and Avogadro number in chemical calculation. It is also expected that by the end of this lesson that you should be able to perform simple calculations involving formulae, equations, chemical composition, and then the mole concept. So all these are our learning objective, and I want you to please pay a close attention to all that I'm going to be expounding on today, and try to follow along. If you have a question or there's an area that is not clear, all you need to do is to just send them into through the comment section. I will pick them up, I'll clarify or expatiate on them as the case may be. All right. Having said that, let's look at our first slide today. And what's our first slide? Trying to give an introduction. Chemical combination refers to the process where elements or compounds unite to form new compounds. Elements or compounds, they come together, they combine, they unite to form new compounds. That's what chemical combination is. Now, understanding the fundamental laws governing these combinations is crucial for comprehending chemical reactions and stoichiometry. Now, this lesson will cover the essential laws of chemical combination, chemical symbols, formulae, equations, relative atomic mass, the mole concept, Avogadro number, and stoichiometry as outlined in the JAMB chemistry syllabus. Okay. All right, I haven't done the introduction. Let's look at the first law here, the law of chemical combination, the law of chemical combination, the laws rather of chemical combination. And the first law that we want to look at is the law of definite proportion. The law of definite proportion. What does this law state? It states that a chemical compound always contains the same element in the exact same proportion by mass, regardless of the sample size or source. I'll take that again for emphasis sake. The law of definite proportion states that a chemical compound always contains the same element in the exact same proportions by mass, regardless of the sample size or source. Now, for example, water. We all know water, right? Okay. Water consistently comprises of hydrogen and oxygen in which ratio? Ratio 2 to 1 by volume. Whenever you find water, it will always contain what hydrogen and oxygen. And the ratio of their combination is 2 hydrogen against 1 oxygen. Okay. So this law is telling you that a chemical compound will always contain the same elements in the exact same proportion by mass, regardless of the sample size or the source. So wherever you find water, whichever the source of water is, or so whatever, wherever you find it, the combination of hydrogen and oxygen in that water is always in the ratio 2 to 1. Okay. All right. So looking at the law of definite proportion, just pushing it a notch further by looking at this example to buttress, the law that had been stated earlier. Now, the first example one, water, that is H2O, its chemical compound. It contains two elements, that is hydrogen and oxygen. Now, since mass of hydrogen equals 2 grams, H2 equals what 2 grams, and oxygen is 16 grams. Therefore, the ratio of hydrogen to oxygen will be what? 2:16. What we are talking about is that the relative atomic mass of hydrogen is 2 grams, and that of oxygen is what? Is 16. So therefore, the ratio of hydrogen and oxygen that makes up water will be ratio 2 to 16, 2 from hydrogen and 16 from oxygen. So the ratio will be now ratio 1 to 8 when you divide all through by 2. So you have what? Ratio 1 to 8. Now, these two elements are always constant. They are always in constant proportion by mass, which is 1:8. That is, there will always be 1 gram of hydrogen and 8 gram of oxygen. There will always be what? 1 gram of hydrogen and 8 gram of oxygen, wherever you find water combining, hydrogen and oxygen combining to form water. Now, it does not matter the source of water, whether it is tap water, whether it is water from river or ocean water or produced by any chemical reaction, melting, cooling of ice, and so on and so forth. It is fundamental. It will always exist in the ratio 1 to 8. 1 of what? Hydrogen against 8 grams. 1 grams of hydrogen against 8 grams of oxygen. Now, when you look at the simple analogy that is here, you have hydrogen bonding together with oxygen in that manner. And when they bond together, you have 2 molecules of hydrogen, plus oxygen, 1 molecule of oxygen to give us what 2 molecules of water. Now, what you have there in the combining ratio is that we have 4 grams of hydrogen. How did we arrive at that? 2 times 2, that will give us 4. The relative atomic mass of hydrogen is 1. So that will give us 4 grams. For oxygen, it is 16, but when we have a subscript of 2. So because of that, it is 2 multiplied by what? By 16. So that is 32 grams. So the ratio now becomes what? 4 grams against 32 grams. When you divide all through by 4 grams, what you end up having is ratio 1 to 8 by mass. So you end up having what? Ratio 1 to 8 by mass. This is a definite proportion for water anywhere, regardless of the sample size or the water source. Okay, having said that, let's push this a bit further. Now, when you look at carbon dioxide is another one that we can use as our example here. When you closely look at carbon dioxide, it said carbon dioxide can be obtained by different methods, such as by respiration. It's a byproduct, of respiration. Then eating limestone will give us carbon dioxide. And then by eating sodium bicarbonate, will also produce carbon dioxide. And then by the action of hydrochloric acid dilutes on calcium carbonate, this will produce CO2 also. Now, it has been observed that CO2 obtained by every method contains carbon and oxygen. And the carbon and oxygen is always in the ratio what? 12 to 32. How do we arrive at this? The relative atomic mass of carbon is 12, that of oxygen is 16. But because we have O2, so it will be 2 multiplied by 16, that will give us 32. All right. Now, so the ratio is always in ratio 12 to 32. Ratio what? 12 to 32. All right. Now, when you break that down further, you can divide both sides by 8 or divide through rather by 8. Now, when you divide through by 8, the ratio of carbon to oxygen in any instance that you have carbon dioxide forming is ratio 3 to 8. That's a definite proportion, ratio 3 to 8 by weight. Now, I haven't done or shown you these two examples. I want you to try this out for me as your class activity. Once you solve it, just put it in the comment section. I will look through it and I will review accordingly. Okay. Now, state various methods for obtaining the following. State various methods for obtaining the following. Number one, SO2, and the second one is NO2. NO2. Okay, so you state the various methods for obtaining them. Then also determine if they obey the law of definite proportion. So I want you to work it out for me and let me know in the comment section if they obey the law of definite proportion. Okay, so make sure you engage. It's very, very important that you engage so that you can actually be sure that you understand the concept of definite proportion as I've explained it. All right. So we move on now to the next law, and it is called the law of multiple proportion. The law of multiple proportion was proposed by John Dalton in 1803. Now, this law states that if two elements combine to form more than one compound, the mass of one element that combined with a fixed mass of the other are in ratios of small whole numbers. Now, take notes. If two elements combine to form more than one compound, the masses of one element that combine with the fixed mass of the other are in ratios of small whole number. For instance, carbon and oxygen form CO, that's carbon monoxide, and carbon 4 oxide, CO2, with mass ratio of oxygen combining with a fixed mass of carbon being 1:2. 1:2. So what happened is that it's the carbon, the mass of carbon that is combining is fixed, but that of oxygen is varying. But when you still work it out, you still discover that it will always still result in ratios of small whole numbers. And that's why we arrived at 1:2. Okay, let's look at an example to explain this further. Now, carbon monoxide, CO, 12 parts by mass. What I mean by 12 parts is that it has a relative atomic mass of about 12, you understand? So 12 parts by mass of carbon combines with 16 parts by mass of oxygen. Hope you still understand what I'm just explaining. I guess you should. 12 parts. 12 is the relative atomic mass of carbon. 16 is the relative atomic mass of oxygen. So 12 parts of by mass of carbon combines with 16 parts by mass of oxygen. Okay, that's for carbon monoxide. Now for carbon dioxide, CO2, what we have operating there is 12 parts by mass of carbon combining with 32 parts by mass of oxygen. Now, if you look at it closely, you discover that a particular element is fixed while the other one is varying. But when you work it out, you still discover that the ratio that you should get will be a whole number. And that's why the ratio of masses of the masses of oxygen that combines with the fixed mass of carbon, 12 parts now, is ratio 16 to 32. How did we arrive at that? Carbon is constant, 12 parts for in both carbon monoxide and carbon dioxide is what is combining. But the oxygen is varying. You have 16, parts of by mass of oxygen combining with carbon to give us carbon monoxide, and then 32 parts by mass of oxygen combining with 12 parts by mass of carbon to give us CO2. So what we have there is a varying oxygen. So the ratio is ratio 16 to 32, 16 to 32. And if you look at it and you divide through, by 16, what you end up having is what ratio 1 to 2. So it still gives us what a whole number, ratio 1 to 2, so to speak. So that is what the law of multiple proportion stipulates, or that is what the law of multiple proportion states. Now, when you have the mass of carbon to be 12U and the mass of oxygen to be 16U, so we can say that 12 grams of carbon combines with 32 grams of oxygen to form what? CO2. Similarly, we can also say that 12 grams of carbon combines with 16 grams of oxygen to form CO, carbon monoxide. So the ratio of oxygen in the first and the second compound is ratio 2 to 1. Ratio what? 2 to 1. That is 32 divided by 16, which is equals to 2, which is a whole number. So this establishes or affirms the law of multiple proportion. You have a fixed mass of carbon combining with a varying mass of oxygen. But when you go through the ratios that will result after doing the calculation, you still discover that it will give you a whole number. And that is what this law is trying to establish. Okay. All right, so let's move on to the next slide now. Still on the law of multiple proportion. Now, another example. Hydrogen and oxygen are known to form two compounds. The hydrogen content in one is 5.93%, and that of the other is 11.2%. Show that this data illustrates the law of multiple proportion. Show that this data illustrates the law of multiple proportion. Now, in the first compound, hydrogen is what? 5.93%. That means the oxygen content in that particular compound is what? Subtracting 5.93%, which is the percentage of hydrogen, from 100. Don't forget that hydrogen and oxygen is what makes up the compound. So when you look at it holistically, the total amount of when you had hydrogen content and oxygen content should be equal to 100 because it's a percentage, right? So if the content contains hydrogen in 5.93%, so we can easily calculate out that which the component or the composition of oxygen in that compound would be, just subtracting the composition of hydrogen from 100. And that was what we did here, 100 minus 5.93 to give us a 94.07%. And this is what's called the percentage of oxygen in that particular compound. So in the first compound, the number of parts of oxygen that combines with one part by mass of hydrogen is what? 94.07, which is the percentage of oxygen, divided by 5.93, which is the percentage of what? Of hydrogen. And that will give us 15.86 parts. So it is 15.86 parts of oxygen that will combine in the first compound. Okay. Now, in the second compound, we were told that hydrogen has a composition of 11.2%. Just like what we did in the previous one, we subtract 11.2% from 100. So when we do that, the content that will remain will be 88.88%, which is the percentage for oxygen in that particular compound. So in the second compound, the number of parts of oxygen that combine with one part by mass of hydrogen is 88.88 divided by 11.2. And that gives us what? 7.9 parts. 7.9 parts. If you punch the calculator, you arrive at 7.9 parts. Okay, now having said that, now the ratio of the masses of oxygen that combined with fixed mass of hydrogen is ratio 15.86 from the first compound against 7.98 in the second compound. Or basically, when you do the division through, a ratio of 2 to 1, a ratio of what? 2 to 1. This is consistent with the law of multiple proportion. A whole number, a ratio that's of a whole number will always be arrived at. So this law is in conformity with the law of multiple proportion. Please, if you don't understand what I've explained, put them in the comment section, your questions, and then I will address it. But I've tried as much as possible to make it as simple as I can so that everyone can actually understand and get, the explanation clearly. But if there's an area that you don't still understand, please put in the comment section and then I will address it appropriately. Thank you. All right, let's move on now to the law of reciprocal proportions. The law of reciprocal proportion. Now, this law states that if two different elements combine separately with a fixed mass of a third element, the ratio of the masses in which they do so will be the same or a simple multiple of the ratio in which they combine with each other. Now, the law states that, now break it down. If two different elements combine separately with a fixed mass of a third element, the ratio of the masses in which they do so will be the same or a simple multiple of the ratio in which they combine with each other. Now, for example, if element A combines with element B and element C separately, the ratio of the masses of B and C, excuse me, please, that combines with a fixed mass of A will be the same or it will exist as a simple multiple of the ratio in which B and C combine with each other. That is what the law of reciprocal proportion states. Now, let's look at this example to explain this law. Oxygen and sulfur react with copper to give copper oxide and copper sulfide respectively. Sulfur and oxygen also react with each other to form SO2. Now, if you look at it, you have oxygen, you have sulfur, you have carbon in the mix, and they are reacting and they are forming different compounds separately. Now, let's look at this and let's use it to explain the law of reciprocal proportion. Now, what you have in copper and sulfur is that you have copper sulfide, and the ratio is copper combining with sulfur. The relative atomic mass of copper is 63.5, and that of sulfur is 32. Now, that's in CUS. Now, that's copper sulfide. Now, in copper oxide, copper is combining with oxygen, and the ratio is that is 63.5 against 16. 63.5 against 16. All right. Now, when you look at it closely, you discover that the copper seems to be fixed in all this. The relative atomic mass is still reflective, but that of sulfur and oxygen varied. Sulfur and oxygen varied. And what is the variation? You have ratio 32 against ratio 16, against 16 rather. 32 against ratio 16. Is that also? Yes, it is, based on what we have there, as the relative atomic mass. Now, when you divide through by 16, the ratio of sulfur to oxygen that you have there will be ratio 2 to 1. Ratio 2 to 1. That's the ratio that you have there. Now, if you look at a combination of sulfur and oxygen, which is the second one, to give us sulfur 4 oxide, sulfur and oxygen combining, the relative atomic mass of sulfur, like I said earlier, is 32. That of oxygen is 16, but it is carrying a 2. So because it is carrying a 2, just like what you can see on that screen there, it means that it will be 2 times 16, that's 32. So the ratio of sulfur and oxygen that will combine to give us SO2 will be ratio 32 against 32. Now, when you divide through by 32, what you end up having is that sulfur and oxygen will combine the ratio 1 to 1. It's combining the ratio what? 1 to 1. Thus, the ratio between the two ratios, the ratio between the two ratios is the following. For the first part of the question, the ratio is 2 to 1. That is copper sulfide and then copper oxide, right? Is ratio 2 to 1 as calculated. But that of the second part, when you find sulfur reacting with oxygen to give us SO2, is ratio 1 to 1. So it is ratio 2 divided by 1 against ratio 1 against, divided by 1, so to speak. So what you end up having is what is ratio 2 to 1. And this is in line with the law of reciprocal proportion because this is a simple multiple ratio. It's a simple what? Multiple ratio. So you end up having that. So that is what the law of reciprocal proportion is. If you want us to, I can go back and just say this so that to bring it back again, adventure you had forgotten how we stated the law, so to speak. So he said this law states that if two different elements combine separately with a fixed mass of a third element, copper is combining with sulfur and oxygen in the first instance, just like we just calculated. So if two different elements combine separately with a fixed mass of a third element, the ratio of the masses in which they do so will be the same or a simple multiple of the ratio in which they will combine with each other. You understand? And that was what we just did here. Copper sulfur and copper sulfur, copper sulfide, copper oxygen. The ratio after going through all that is, excuse me, please, ratio 2 to 1. That's sulfur to oxygen there is what ratio 2 to 1, because it's the sulfur and oxygen that is varying, like I explained before. Now, a whole different compound like SO2, whereby sulfur and oxygen is combining together. Now, when they combine, the ratio is what ratio 1 to 1 that you end up having. But when you look at it closely, for sulfur and oxygen in involving copper and all that, against this sulfur and oxygen, when they combine together, it's just ratio 2 over 1 divided by ratio 1 into 2 divided by 1, ratio 1 divided by 1. So ratio 2 to 1. So this is a simple multiple ratio. And this establishes the law of multiple proportion. Okay. The next one is the law of conservation of matter. The law of conservation of matter. And this law was formulated by a man. The name of the man is Antoine Lavoisier. That's the name of the man. That's the name of that man that formulated that particular law. Sorry, I had a little a little glitch, and then I will continue from where I stopped. I was talking about the man called the man called Antonio Antoine Lavoisier, right? Antoine Lavoisier. That was the slide I was on, and I believe that was the law of conservation of matter. So please pardon me. Let me just go back and start from there. I had a little glitch in my connection, and I had to sort it out. So I've sorted it out now. So we can continue. Let me just quickly. Okay, so I said the law of conservation of matter was formulated by Antoine Lavoisier in 1789. And then this law states that matter is neither created nor destroyed in a chemical reaction. Now, the total mass of reactants equals the total mass of product. For example, when hydrochloric acid reacts with sodium hydroxide to form water and sodium chloride, the total mass of hydrochloric acid and sodium hydroxide before the reaction equals the mass of water and salt produced. Do you understand that? So you cannot create matter, you cannot destroy it. It's just like what the book say in the world of computer, that garbage in, garbage out, so to speak, you know. So that is what the law of conservation of matter, stipulates or yes, states. Okay. Look at this example to buttress the law of conservation of matter. Potassium hydroxide, KOH, readily reacts with carbon dioxide, CO2, to produce potassium carbonate. That's K2CO3 and water. How many grams of potassium carbonate is formed if 224.4 grams of KOH react with 88.0 grams of CO2? The reaction is also the reaction also produced 36.0 gram of water. Okay, now let the gram of potassium carbonate produced be X, because that's more like what we are looking for. So we're told from this question that 224.4 grams of potassium hydroxide reacted with 88.0 grams of carbon dioxide to give us X grams of K2CO3 and then 36 grams of water. Okay. So on the reactant side, when you add up what is on the reactant side, what you end up having is about 312.4 grams of the reactant. And then on the product side, what you have is S grams of K2CO3 plus 32 grams of H2O. Now, for us to know the mass of K2CO3 that was in the that was formed, is simply to remove or to deduct or subtract 36 from 312.4 grams from the reactant side. And that will give us the mass of the K2CO3 now. So therefore, the mass of K2CO3 will be what, 276.4 grams. So when you punch your calculator, you do that little subtraction, what you end up having will be 276.4 grams of potassium carbonate that was formed. Now, the reason why we can easily do this equation, or we can equate this to the reactant against the product, is because the law of conservation of matter states that clearly that, matter cannot be created nor destroyed. So that means what I put in the reactant side is what I will most likely get out in terms of mass now in the product side. So I can easily just do a subtraction to know what is missing, and then the mass of whatsoever, either reactant or product, that was not stated, or that was used up, or that was produced, as the case may be. Okay. All right. Having said that, let's talk about Gay-Lussac's law of combining volume. Now, this was established by Joseph Gay-Lussac in 1808, and this law states that when gases react together at constant temperature and pressure, the volumes of the reacting gases and the volume of any gaseous product are in simple whole number ratio. They are in simple whole number ratio. For instance, two volumes of hydrogen gas react with one volume of oxygen gas to produce what? Two volumes of water vapor. So what you have is 1:1 to give us ratio what? 2 of what's it called, of the of the water vapor. The same thing happens with hydrochloric acid. Hydrogen one volume, chlorine one volume, combining them to give us two volumes of hydrogen chloride or hydrochloric acid, as the case may be. Now, looking at this example now, just like we stated, two hydrogen plus oxygen give us two H2O. Now, the question is, what volume of steam is formed from 20 cm cube of hydrogen and 20 cm cube of oxygen if they are mixed together? So, what volume of steam will be formed? The second one says that what gases is in excess and by what gas or gases are or is in essence and by what volume. So, solution to question A. Now, the ratio of their volume is ratio 2 volumes against 1 to give us 2 volumes. So, ratio 2 to 1 to 2, in that regard. So, you have 20 same cube of hydrogen, and it is combining with oxygen. But this oxygen in this regard will be just 10 volumes because don't forget that it's existing in ratio 1 and hydrogen is existing in ratio 2 to give us 20 volumes of water or steam as the case may be. Okay, that means 20 cm cube of hydrogen will combine with 10 cm cube of oxygen to form 20 cm cube of steam. That's the implication. That's the volume, that the combining volumes now. Now, for us to be able to know, oxygen is in excess by 10 cm cube. Because what happens is that instead of us using up 20 cm cube that was mixed initially, what we end up taking up with what? Just 10, because it's just one volume of oxygen that is involved in that combination. So you'll be left with 10, excessive oxygen, 10 cm cube excess oxygen in that particular scenario. Okay, all right. So the next one is Avogadro's law. And Avogadro's law states that the volume of a gas is directly proportional to the number of moles of gas when the temperature and pressure are held constant. When the temperature and pressure are held constant. You can equally say that equal volume of all gases, under the same temperature and pressure contains the same number of molecules. That's another way to state this also, but mathematically we can express Avogadro's law to be volume equals to a constant, which is K multiplied by N, and then V1 over N1 equals to V2 over N2, where N is the number of moles of gas and K is a constant. Let's look at this example. A balloon has been filled to a volume of 1.90 liter with 0.0920 moles of helium. If 0.0210 mole of additional helium is added to the balloon while the temperature and pressure are held constant, what is the new volume of the balloon? So looking at that one, the first one is that we list the known quantities and plan the problem. What are the known quantities? We're given a first volume or initial volume, as the case may be, to be 1.90 liter. Then we're given a number of moles. The first one that was given to us, N1, your initial is 0.0920 mole. And then your N2 is simply 0.092 plus 0.0210. Why do we have to do that? Because it said if 0.021 mole of additional helium is added to the balloon, why the temperature and pressure are held constant, what is the new volume of the balloon? So the N2, or the final what's it called, number of moles now will be what? The initial plus the final. That will give us 0.0920 plus 0.0210 to give us 0.1130 mole. Okay. All right. So having established the known, let's look at the unknown. Note that the final number of moles has to be calculated by adding the original number of moles to the moles of added helium. Now, we can now use Avogadro law to solve for the final volume. Now, the first thing is that we need to rearrange the equation algebraically to solve for V2. So when you rearrange, you make V2 the subject of the formula, you end up having V2 to be V1 multiplied by N2 over N1. Now let's substitute the value or the values now based on the known quantities now. we have the initial volume to be 1.90, then we have the final number of moles to be 0.113 moles, and then the initial number of moles to be 0.092 moles. So when you go through this, you end up having a volume of 2.33. Okay, 2.33. All right. So that is pretty straightforward. Understand the formula, try to establish those parameters that are known, and then try to establish those that are not known, and then look for the unknown from there, and you'll be able to arrive at your answer. Very simple. Okay. So the next thing that we need to look at is Avogadro's number and the moles. Now, the Avogadro's constant is given to us to be 6.02 times 10 raised to the power 23. It is a constant. It is universal. That is the number all over the world. 6.02 times 10 raised to the power 23. It is also referred to as the Avogadro number. It is also referred to as the Avogadro number, denoted with the symbol Na. It means that there are 6.02 times 10 to the power 23 particles in 1 mole. Now, take for instance, there are 2 times 6.02 times 10 to the power 23 in 2 moles of water molecules. So if you have 2 moles of water molecule, what's it called, for us to be able to know the number of moles that will be contained therein is just for us to say 2 times 6.02 times 10 to the power 23. So that's that for that. So it's pretty straightforward. If it is 4 times 6.02 times 10 to the power 23, like that, and so on and so forth. So another concept that is important is mole, and mole is defined as the amount of substance, that the amount of a substance. Yes, that's the mole. The amount of a substance is what we refer to as the mole. Okay, it is denoted with the letter N. It is denoted with the letter N, and it is used to count the number of particles. It is used to count the number of particles, and then the unit for moles is mol. That's the unit. And 1 mole of a substance contains the same number of the stated particles. 1 mole of a substance contains the same number of the particles. And that's why I said, okay, if you have 2 moles of water and then you want to know the number of particles that it contains, you say 2 times 6.02 times 10 raised to the power 23, so you know the number of particles. So what this is just establishing is that if you have a mole of a substance, it will contain the same number of the stated particles, atoms, molecules, or ion as 1 mole of any other substance. Okay, all right, that's good. So the next thing that we need to look at is the molar mass. And before we look at the molar mass, you permit me to start off with the relative formula mass. The relative formula mass. The relative formula mass is the sum of the average atomic masses. The sum of the average atomic masses of all atoms represented in a chemical formula, and it is expressed in atomic mass units, AMU. So the relative formula mass is the sum. So when you have HCl, the relative formula mass will be what? The sum of the atomic masses of hydrogen and chlorine. So that is what forms what the relative formula mass. Now, the relative formula mass is dimensionless. It's a dimensionless quantity, meaning it has no unit. Now, the molar mass, on the other hand, refers to the mass of 1 mole of a substance, that is either an element or a compound, and is expressed in grams per mole. It is expressed in grams per mole. Now, it is calculated by summing the standard atomic weights of the constituent elements in a compound, summing up the standard atomic weight of the constituent elements in a compound. Don't worry, don't get confused by all the big or the English. We're going to bring it down by looking at some examples to explain or to make this much clearer. So let's look at this relative formula mass calculation now. Example, what is the relative formula mass of sodium chloride? What is the relative formula mass of sodium chloride? Don't forget that for sodium chloride, you have sodium, then you have chlorine. So it means that the relative atomic mass of sodium is 23. We know that before, it's 23. Whereas the relative atomic mass of chlorine is 35.5. So what we do is that we sum it up, the average atomic masses of sodium, and chlorine. When you sum it up, you have 58.5, and it does not have a unit, it is dimensionless, like we stated earlier. The next one says that what is the relative formula mass of water molecule? Now, don't forget that the relative atomic mass of hydrogen is 1, the relative atomic mass of oxygen is 16. So therefore, calculating and then summing up the average relative atomic masses, you end up having 16 based on that on that calculation. You end up having 18, please pardon me, based on the calculation that you have there on the screen. So we should take note of that. It's important. Yeah, so I gave a class activity for you to try. So I want you to get that your pen and your paper out again and do this little calculation. What is the relative formula mass of the following? Barium chloride, hydrogen fluoride, and then potassium chloride. So work it out and then put your answers in the comment section. I will look through it, I will review it accordingly and respond to it. All right. So I believe this is pretty straightforward. You should be able to do it, but just work it out. Let me be sure that you get the concept. So we move along now to calculation of molar mass. Let's look at the first example. What is the molar mass of sodium chloride? Now, the molar mass of sodium chloride is just bringing together the relative atomic mass of sodium and then that of chlorine together. When you combine them together, then you multiply it by 1 gram per mole, and that's the difference now. So we've established before that the relative formula, what's it called? We've established that the relative formula mass of sodium chloride is 58.5. So for us to be able to get the molar mass, you just multiply that by 1 gram per mole in order for us to bring the units in. So the molar mass of sodium chloride is actually 58.5 gram per mole. Now, the next example says that what is the molar mass of magnesium carbonate? Magnesium carbonate, the same thing. You calculate the relative formula mass, and then from there you multiply by 1 gram per mole, and you end up having 84 gram per mole. Okay, all right. So that's that. We want to look at relations or calculations, please. Calculation involving amount of mole, sorry, amount of substance, relative atomic mass, and relative formula mass. Amount of substance, relative atomic mass, and relative formula mass. Now, when you look at it, mass equals to mole multiplied by molar mass. That's the connecting formula. Mole multiplied by molar mass. Therefore, our mole equals to mass divided by molar mass. So we established this. So look at this example now. How many moles are there in 64 grams of oxygen? How many moles are there in 64 grams of oxygen? Now, the mole there, don't forget our connecting formula, mole equals mass divided by the relative formula mass, or sorry, the molar mass now, the molar mass, okay? All right, so if you look at it closely, the mass that was given to us is 64, and the relative formula mass of oxygen in that regard is 16 times 2. So that would be 32. So it will be 64 divided by 32. So the number of moles that will be contained in 64 grams of oxygen will be 2 moles, will be 2 moles. The second example says, how many grams are in 5 moles of ammonia? How many grams are in 5 moles of ammonia? Now, what are the things that we know? We know the number of moles to be 5 moles. We know the molar mass to be 17 gram per mole, 17 gram per mole. So therefore, we can calculate the mass by saying that mass equals to mole multiplied by molar mass, and then the mass equals to 5 times 17, which is 85 grams, which is 85 grams. So we've established that, so we can get the mass out. Even if you're given the mole, you can get the mass. If you are given the mass, you can get the mole out. If you are given the mass and the mole, you can actually get the molar mass out too, using this connecting formula to do that. Okay. Now let's look at some stoichiometry. Look at mole-mole relationship, and look at this question as an example. It said when 2 moles of nitrogen react with sufficient hydrogen, how many moles of ammonia will be produced? Let's look at the equation. The equation is stated there. 2 moles of nitrogen react with sufficient hydrogen. How many moles of ammonia will be produced? Now, step 1. in solving this problem is that we will use this ratio to set up the proportion. We use this ratio to set up the proportion. So we say that it is ammonia against what? Nitrogen. A ratio of ammonia against that of nitrogen. That means that the ratio from the equation is what? 2 moles of ammonia against 1 moles of nitrogen based on the equation that is up there. Now, step 2, the ratio from the data in the problem will be what? X over 2 moles of nitrogen, because we're told that when 2 moles of nitrogen react with sufficient hydrogen, how many moles of ammonia will be produced? So from the equation, we were able to establish that it is 2 moles of ammonia that will be combining to with what? 1 mole of nitrogen. But from the question, we can also establish that it is what? X mole of ammonia, because we don't know, that will be combining with 2 moles of nitrogen. Now, step 3 is for us to equate these two, ratios together. We equate step 1, then we cross multiply. So NH3 over N3 equals to X over 2 mole of nitrogen. When you cross multiply, you have 1 mole of nitrogen being multiplied against X equals to 2 moles of nitrogen multiplied by 2 moles of ammonia. Okay, so our X now, making it the subject of the formula, will have 2 moles of ammonia divided by 2 moles of nitrogen divided by 1 mole of nitrogen. Okay, so that means our X will be 4 moles of ammonia that will be produced. So we have been able to establish that just using mole. So we can find that the mole of ammonia that will be produced is 4 moles that will be produced. Okay. All right, let's look at another example and talk about ammonia nitrate decomposes to dinitrogen monoxide and water according to the following equation. And then the equation is what you can see there. In a certain experiment, 45.7 gram of ammonium nitrate is decomposed. Find the mass of each of the products produced. Each of the products produced. So in solving this problem, we'll take the steps. First, list the known quantities, and then we can now look at the problem. So basically, the known quantities are 1. We are given 45.7 grams of ammonium nitrate. 1 mole of ammonium nitrate equals to 1 mole of nitrogen, dinitrogen monoxide, according to the equation, and equals to 2 moles of water based on the equation. Now, the molar mass of ammonium nitrate is 80.06 grams per mole. You can work it out, you will arrive at 80.06 grams per mole. The molar mass of dinitrogen monoxide is basically 44.02 grams per mole. And then the molar mass of water is 18.02 grams per mole. Okay, now those are the known. What are the unknown? We don't know the mass of the nitrogen monoxide, and we equally don't know the mass of water that is, that is used up, or that was used in this particular reaction. So we need to figure those ones out. So we perform 2 separate 3-step mass calculation as shown below. We look at it. Ammonium nitrate will go forth to give us size. That is the mass of ammonium nitrate will give us the mole of ammonium nitrate to the mole of dinitrogen monoxide, and then the mass of N2O, that's dinitrogen monoxide. And then the second one is that the gram of the mass of ammonium nitrate to the mole of ammonium nitrate to give us the mole of water, and then the mass of water. So those are the things that we need to, the relationship that we need to, we need to establish, so to speak. So we must establish that. So now don't get confused. Just look at it and look at the question, look at the equation, and then you follow through, and then you get all that I'm trying to explain. It is pretty simple. It's not difficult. Just open your mind and look closely at the question and the step-by-step method that we are using to solve the question. So step 2 is to solve now. And for us to solve, I'll bring in the actual value of some of this component that I've stated up there. So it is 45.7 grams of ammonium nitrate that will be reacting against 1 mole of ammonium nitrate over the mass of ammonium nitrate, which is 80.06, multiplied by 1 mole of N2O divided by 1 mole of NH4NO3, that's ammonium nitrate, multiplied by 44.0 grams of N2O over 1 mole of N2O, and that will give us 25.1 gram of N2O. That's what we'll get. Now, in the same vein, if 45.7 gram of NH4NO3, it combines in the mole of ammonium nitrate divided by 80.0 grams of ammonium nitrate multiplied by 2 hydrogen through water, 2 water divided by 1 mole of NH4NO3 multiplied by 18.0 grams of water divided by 1 mole of H2O. What you end up having there will be 20.6 grams of water, 20.6 grams of water. Okay, so we can find the mass of N2O, or we have found the mass of N2O to be 25.1 and that of water to be 20.6 grams. Okay, the next relationship that we need to establish is the volume-volume relationship. Avogadro's hypothesis states that equal volume of all gases at the same temperature and pressure contain the same number of gas particles. Further, 1 mole of any gas at standard temperature and pressure, that's 0 degrees Celsius and 1 atmosphere, occupies a volume of 22.4 liter or 22,400 cm3. Now, these characteristics make stoichiometric problem involving gases as STP very straightforward. Now, let's look at an example. Now, the combustion of propane. Propane is an organic compound. The combustion of propane gas produces carbon dioxide and water vapor. It produces carbon dioxide and water vapor based on the equation that you can see there below. So the question is, what volume of oxygen is required to completely combust 0.650 liter of propane? What volume of carbon dioxide is produced in the reaction? Okay, so let's look at it and solve this problem stepwise now. Step 1, list the known quantities and plan the problem. So we are given 0.650 liter of propane and 1 volume of C3H8 equals what? 5 volumes of O2 based on our equation. So 1 volume of C3H8 will be equals to what? 3 volumes of CO2, also from the chemical equation that we have there. Now, the volume of oxygen, we don't know. That we are stating the unknown now. We don't know the volume of oxygen, neither do we know the volume of CO2. So now 2 separate calculations can be done using the volume ratio. And what are the separate calculations? 0.650 liter of C3H8 will multiply by 5 liters of oxygen, divided by 1 liter of C3H8 will give us what? 3.25 liters of oxygen. So we are trying to bring that and equate them, establish a relationship between them. Equally or similarly, 0.650 liter of C3H8 will give us 3 liters of CO2 over 1 liter of C3H8, which will give us 1.95 liter of CO2. This relationship were just established, or we just took them out from the equation of the reaction. So that is how we go about, volume-volume relationship, establishing the stoichiometry, so we can easily solve and then get our answers out accordingly. But if you are not so, if you don't understand any concepts in regarding what I've explained so far, please ensure that you reach out through the comment section and let me know. Thank you. So I want to look at chemical symbol formulae and then their equation. Chemical symbols are shorthand representations of elements. They are shorthand representation of elements. So when, instead of us writing hydrogen, Hydrogen, we can actually write H for hydrogen and O for oxygen. Okay. Now, chemical formulae denotes the composition of compounds, e.g., H2O for water. That's a chemical formula. H2O for water, SO2 for sulfur dioxide, and so on and so forth like that. Now, chemical equation represent chemical reactions showing reactants transforming into products. So chemical equation represent chemical reaction that shows the reactant transforming into what? Into product. So we have 2H2 plus oxygen to give us 2H2O. Now, balancing chemical equation ensures the law of conservation of matter is what? Upheld. Is upheld. Okay. Now, chemical symbol formula and equations. Now, in balanced chemical equation, the reactants and products must have the same number of atoms. And this is in conformity with the law of conservation of mass. So what we have on the right-hand side is the reactant, and so on the left-hand side, pardon me, is the reactant. Then on the right-hand side, we have the product, just like what you have there. Four molecules of hydrogen will combine on the reactant side and still produce four molecules of hydrogen or 4 moles rather of hydrogens on the product side. And then we have 1 mole of oxygen on the reactant side, still giving us, 2 moles of oxygen on the reactant side, giving us 2 moles of oxygen on the product side. Now, if you look at it closely, you see a 2 behind hydrogen and a 2 behind or in front of water, as the case may be. Now, these are referred to as coefficients. These are referred to as what? Coefficient, just like the arrows pointed them out. They are referred to as coefficient. Now, to balance the number of atoms in an equation, we use coefficients. These are numbers written in front of a chemical symbol or formula. Now, note, we never balance an equation by adding subscripts. Subscript is what you had, whereby you had something below the element. Like when you have oxygen, that you have the 2 below it, that's a subscript. We don't balance by adding subscript. We can only balance by adding coefficients, that is adding a number in front of the element. And that's the only way we are permitted in chemistry to balance a chemical equation. So please, let's take close note of that. It will help us a lot as we progress along. Okay. Now, the next thing that we'll need to look at is the empirical formula. Empirical formula. Okay. And also molecular formula. We start off by looking at what is empirical formula. An empirical formula is the simplest formula for a compound. Is the simplest formula for a compound, which is defined as the ratio of subscripts of the smallest possible number, whole number of the element present in the formula. Empirical formula is also referred to as the simplest formula. Let's look at this example. 0.150 grams of copper react with oxygen to form 0.188 grams of copper oxide. Find the empirical formula of copper oxide. Find the empirical formula of copper oxide. Now, I've used this table beside to explain, the concept. The mass of copper in that particular this thing is 1.21, and that of oxygen is 0.15. 0.15. So the molar mass is 63.5 for copper, and then that of oxygen is 16. Now, mole equals to mass divided by molar mass. So when you divide, you have 0.019 for copper and 0.009375 for oxygen. Now you divide by the smallest number, or by the smaller number rather. So when you divide through by 0.09375, which is the smallest number, the simplest ratio that you get to be ratio 2 to ratio 1. Ratio 2 to ratio 1. That's the empirical formula. Okay. Now the molecular formula is the formula derived from the molecule, and it is representative of the total number of individual atoms present in a molecule of a compound. So basically, molecular formula equals to N multiplied by empirical formula. Molecular formula equals to what? The N multiplied by empirical formula. So N equals to molecular formula or empirical formula. Sorry, molecular formula divided by empirical formula. So you make it N the subject of the formula. So it will become molecular formula divided by empirical formula. Okay. Now, when you look at this example, it said the empirical formula of a compound of boron and nitrogen is BH3. Its molar mass is 28 grams per mole. Determine the molecular formula of the compound. Using that same step to BH3, the molar mass in this regard is 14. Is 14. That's the molar mass. 11 boron plus 1 multiplied by 3 of hydrogen, giving us 14 as the molar mass. And then the second step is to divide 28 by 14. So when you divide it, because from the empirical formula you have gotten, when you add them up, you have 14. So you divide it, and the molecular formula is 2 times of the empirical formula. So in your step 3, all you need to do is just to do what BH3 multiplied by 2, and that will give us B2H6, and that gives us the molecular formula. Okay. Okay, all right. See, so that gives us the molecular formula. All right. So please, at this junction, I want you to just take a little breathe. I want you to just pause a bit. Let's reflect on all that we've been explaining. If you have any question on any of the aspects or concepts I've been explaining, please do well to put them in the comment section so that I can be able to handle them accordingly. Okay, so we move along now to calculations involving the amount of substance, volume, and concentrations in a mole per dm cube of solution. Now, first formula that we need to establish is that concentration equals to mole of solids divided by volume of solution. That's concentration equals to mole of solid divided by volume of the solution. Now, amount of solids is what we refer to as N. Concentration is C in mole per dm cube. Amount of solute N is in mole, MOL. Then the volume of solution V is in dm cube. And don't forget that 1 dm cube equals to 1000 cm cube. Okay, so I would establish this. Let's move into some examples now. 0.03 moles of sodium carbonate is dissolved in 300 cm cube of water. Calculate the concentration of the solution. First and foremost, volume in dm cube equals what? 300 cm cube divided by 1000. So we are just trying to convert 300 cm cube to dm cube by dividing 300 by 1000. That gives us 0.3 dm cube. Okay. Now concentration equals to what? Mole of solids divided by volume of solution, based on the formula that we've established in the previous slide. So that means that it will be 0.03 divided by 0.3 dm cube, and that gives us a concentration of 0.1 mole per dm cube. So I've established some class activity for you to try out. Please look at the first class activity and then the second class activity. Please, I want you to engage them, do them, very, very important. And then when you are done with them, please put your answers, in the comment section. And then I will look at it, review it, and then respond accordingly to them. Thank you very much. Make sure that you do this last activity. That will help you a lot. All right. Okay. So let us summarize what we have learned so far. It has actually been a very, very intensive class, so to speak. So let's try and summarize what we have learned so far. We have talked about chemical combination, and we have defined them that they refer to the process in which elements or compounds unite to form new substances. Okay, so we have established that. We have also tried to explain the laws of chemical combination, the law of definite proportion. We stated it, we gave examples to buttress it. The law of multiple proportion, we stated that we gave examples to buttress it also. The law of reciprocal proportions, the law of conservation of matter. So we also stated those laws, and we gave examples to buttress or to explain them better. Then we also touched on the Gay-Lussac's law of combining volume. So we touched on Gay-Lussac's law of combining volume. We stated what it is, and we gave examples also to explain it further. We've also touched on Avogadro's law, and we stated what Avogadro's law is. We talked about the connecting formula that we can use to calculate, and we also made mention of uh, formula equations. We talked about what formulas are, what the balance equations are. what a balance equation is, how to balance chemical equation. We also looked at the mole concept and then relating the mole concept with Avogadro's number. We talked about what the Avogadro number is. We looked at calculations involving molar mass, the relative formula mass, and then we did a little stoichiometry by looking at relationship of mass relationship, mole relationship, and volume relationship in chemical reactions. And then we did calculations involving empirical and molecular formula. We explained what it is and we gave examples to buttresses. We did a little calculation on concentration, which we say concentration equals to mole of a substance divided by volume of the solution. So we give examples, we applied that formula, we give an example, and then I gave you some class activities to also engage yourself with. Okay, now, having said that, let us try to evaluate this lesson. Please, if you have questions, please put them in the comment section. I will look at it, I will respond to them accordingly. But permit me to evaluate this class with this following question. Now, the first question is what you have on your screen there. Now, look at the question, look at the options that we have, and tell me which is the correct options there, or the correct option rather, in the options provided. So put it in the comment section, and then I will pick it up and then I will respond accordingly. That's the second question. You can also look at it, which of the following is an example of the law of definite proportion? The options are stated there. Kindly look at it and then tell me what the answer is and put them in the comment section, and then I'll tell you whether you're right or you're wrong. Okay, but I think everybody should get it because these are some of the things that we've been treating since. Okay, which scientists proposed the law of definite proportion? So tell me. Look at this question number 4. 100 grams of sample of calcium carbonate contains 40% of calcium, 12% of carbon, and 48% of oxygen. What will be the percentage composition in a 250-gram sample? So tell me what that is. Questions on multiple proportion is another thing that you can also pick up. And look at the options and respond by giving me the right answer in the comment section. Okay. All right. See, so conservation of matter. There's a question on conservation of matter. So you can actually pick it up and then respond accordingly and let me know what your answer is. Okay. All right. See, so these are questions on the Lusak law of combining volume. Also, question on Avogadro's law. I've went gone through the pain of looking at different what's it called questions that you can actually try out. So please, you'll be doing yourself a whole lot of injustice if you don't engage with these questions and give me what you feel your right options are so that I can be able to correct if there's a need for correction or applaud if you get it right. So please look through the questions and respond accordingly and to the questions or engage them accordingly and then I will respond accordingly. Yes, that's it. So that's that. So these are questions on mole concept and Avogadro's number. These are questions on molar mass and relative formula mass. So you can look at it and then you can supply the answers to. Okay, stoichiometry, the mass relationship, the mole relationship, and all the other relationships, we've drawn out questions to that effect. So please, I want you to look through the questions very well. You can see I've actually, gone through the pain of looking out for so many questions for you that touches on every aspect that we have treated. Because I know it's a calculation-based topic, so I want you to also try your ends on this question so that you can be sure that you understand the concept and you can stand anywhere and say, yes, I know this and I know it very well. So please engage the questions, put your answers in the comment section, and then I will react to it accordingly. Okay, thank you so very much for watching, and I hope to see you again in the next class. Thank you. Take care of yourself. I will call it a day today. All right. See you in the next class.